Okay, so now we're going to talk about sort of the recursion tree method to help work out recurrence relations. Uh, the, uh, the substitution method's great. It helps us to get answers if we already know what the answers are. I mean, it's sort of this guess the answer, prove that your answer is true. That's perhaps not the most satisfying thing. Where do the guesses come from? Okay, so sort of let's take a couple examples that we've already seen. So if we start with this recurrence relation, t of n is less than or equal to t of n minus 1 plus 1, where did we get our big O of n guess from? Right? We wanted to prove t of n is less than or equal to c times n. So where do we get it? Well, basically what we do is we say, oh, let's assume that we know answers are of this form, and I'm going to inductively, recursively plug in smaller terms to get rid of them. So I'm given this term, and what I'm going to do is I'm going to say, hey, I know that t of n minus 1 is less than or equal to t of n minus 2 plus 1. So I'm going to plug that in. Great. Hands are done. We're totally ready to go. We've gotten rid of our recursive term. Well, except we replaced it with a different recursive term. So now, great, we know t of n is less than or equal to t of n minus 2 plus 1 plus 1. We want to get rid of that recursive t of n minus 2 term. How do we do that? Well, we use the same form equation. We get rid of it by substituting in, all right? So great. Again, we've gotten rid of our recursive term, and now we have t of n is less than or equal to t of n minus 3 plus 1 plus 1 plus 1. We can keep on substituting in, and obviously, after a while, we're not really getting rid of the recursive form, but we sort of do probably see a pattern at this point. So first of all, we could simplify things. Now that we've simplified, let's stick it into a nicer form. These are the nice simplified forms. We know just by substituting in that t of n is less than or equal to all of these things here, right? And in this case, it's pretty easy to see the pattern, right? We think, hey, t of n looks like it's less than or equal to t of n minus I plus I for an arbitrary integer I. Let's say positive integer I. So great. That gives us a more general form, and we still want to get rid of our recursive term. We still want to get rid of t of n minus I, right? So that's what we're going to do. We're going to substitute in, except instead of using this format to substitute in for t of n minus I, what I'm going to do is I'm going to substitute in an I value to make t of n minus I disappear. I'm going to plug in this case, I equals n. Because if I equals n, we're saying this is true for any I. If we set I equal to n, then this equation reduces to t of 0 plus n. Hey, t of n is less than or equal to t of 0 plus n. Assuming that the time to run the input of size 0 is constant, then I have t of n is less than or equal to that constant plus n. And O of n looks like a great guess. So now we could either take it from here, O of n is our guess. Let's prove t of n less than or equal to t of n minus 1 plus 1. Let's prove that that is big O of n. Well, we already saw that last time. Well, why not just use this thing here as a proof? Do I have a proof on the screen right now? No, not exactly. What's wrong with my proof right now? Well, this line, a little suspect. Generally proofs shouldn't have lines in them that say looks like, or seems to be, or I feel like I recognize a pattern. So it's tough to call that line a proof. Now what we could do is prove that this, that this thing holds, prove that this line holds. We could prove that inductively. And besides that one line, everything else here looks great. Everything else here looks like a fine proof, okay? So let's prove this line inductively. Let's prove that t of n is less than or equal to t of n minus I plus I. We can prove that inductively. The induction now isn't on n. The induction is on I. We plug in I equals 1. Well, we have our base case. How do we know? Well, we're given that t of n is less than or equal to t of n minus 1 plus 1. We're actually given the base case. Right? That's how the recurrence relation is presented to us to begin with. Now, given that this relationship holds for some arbitrary I, we need to show that the relationship holds for I plus 1. Okay? So how do we do that? We know it holds for an arbitrary I. Using our relationship where I plug in n minus I for x, I know that this term is going to be less than, well, here's plugging in my n minus I for x. I still have my plus I term at the end, right? And then I just do some algebra, I work that out, and I have t of n minus 1 plus I is less than or equal to t of n minus I plus 1 plus I plus 1. That's exactly what I'm trying to prove, okay? So I have given the inductive statement t of n is less than or equal to t of n minus I plus I. I've proven t of n is less than or equal to t of n minus I plus 1 plus I plus 1. That's what we prove. Our proof by induction is done, right? So that's great. Everything else about the proof, what is going on here? Everything else about the proof just carries through just like before. This is exactly the same stuff that was in the proof before. Everything carries through just like before. And we have a a fine proof that that our t of n is less than or equal to t of n minus 1 plus 1. I notice I'm covering up a little bit of the text, but oh well, sorry. So, great. Now I've proven that this relationship t of n is big O of n. I've proven it without using substitution, just proven it inductively. Let's do at least one more example. So here we go. Here's another thing that we already saw, our merge sort relation, right? We have t of n less than or equal to 2 t of n over 2 plus n. Where did our n log n guess come from? We're going to do the same thing we did before. We're going to use this sort of general form to get rid of our recursive forms. Hey, I want to get rid of t of n over 2. I use this relation. T of n over 2 is less than or equal to 2 t of n over 4 plus n over 2. Great. Plug that in. Hey, I want to get rid of t of n over 4. I'm going to use this x equals n over 4, substitute in for t of n over 4 using this relation, and I'm going to get the next term and the next term. Now what I can do, just like before, I can sort of simplify all of these things out, get rid of all the math in the middle. Let's look for a pattern here. And again, the pattern in this case is, again, not so hard to see. Hey, it looks like these things look like 2 to the I terms. This looks like t of n over 2 to the I, and this is plus I times n. Okay? How do we get rid of the t of n over 2 to the I term, right? So last time we plugged in, for the other, we plugged in I equals n, and we ended up turning this thing into a t of 0 term. In this case, we can't really turn it into t of 0. On the other hand, if 2 to the I equals n, then n over 2 to the I will be 1, and this term will be t of 1. Oh, that's not so bad. T of 1 again. T of 1 is t of some constant. If we can assume that our runtime is no worse than some constant for any input of size 1, great. Then we're going to be able to just replace t of 1 by some constant. So great, that's what we do. If we know that n over 2 to the I is equal to 1, then we know that I must be log base 2 of n. So this gives us, now plugging in that I, we get 2 to the log n for this term. Well, 2 to the log base 2, that's just n. T of 1 plus n log n. So that equals n times a constant plus n log n. That gives us a good guess, right? So once we have that good guess, we can take one of the two approaches we've seen so far. We can either take the, hey, n log n seems like a good guess. Since n log n is a good guess, we could plug it in for using the substitution method. and just try to inductively, so with the substitution method, prove that T of n is big O of n log n. Or I could get rid of this sort of looks like line and replace this section with a little inductive proof to show me that this line does in fact hold. And if I did that, this would be a complete proof. Okay, that'll be it for today.